All right. So chemistry quiz number 1. Okay. List the points of the atomic theory. Now, they do not have to have these word for word out of the notes. Okay. In fact, it's probably better if you put them in your own words, because then you have to process them and learn them better. Okay. But in general, I'm looking for something along these lines. All matter is made up of atoms. Okay, or tiny particles, or whatever, as long as they have something there about tiny particles and all matter. Okay. Second point. Okay, atoms of the same element are identical, or they may have the atoms of different elements are different. They don't necessarily have to have both, because when you say that all atoms of the same element are identical, that kind of also says that atoms of different elements are different. Okay. Third point, atoms combine in whole number ratios to form compounds. Okay, they got to have something there about the whole number ratios. That was kind of the most important part of point number 3. Okay. And then point number 4 talks about what happens in a chemical reaction. So if they have something about atoms being separated, joined, rearranged, or something about atoms not being changed in a reaction, that would also be fine, okay, because that's essentially what point number 4 is talking about. Okay, questions on number 1? Add or remove. I'm going to have to say no on that one, because that would imply you're making them or destroying them. Oh, if he's got rearranged, yeah, that's good, yeah. But yeah, be careful about saying that in a reaction stuff is added, okay, because that would imply that at the end then you have more than you started with, which violates, of course, the law of conservation of matter, which we haven't talked about, but okay, that's kind of an important thing. Okay, question number 2, who devised this theory? As long as they have Dalton there. If they had John Dalton, great. If they just have Dalton, in science generally we only talk about people's last names anyway. Okay, number 3, name and describe the particles in an atom. Okay, so they should have proton, neutron, electron. Okay, that's not all of it. Okay, so the marking scheme for this one is if they have proton, positive, and nucleus, or just proton positive or proton nucleus. Okay, something about the particle and one other piece of information about it that's correct. That's good. Okay, neutron, neutral, nucleus. Okay, electron, negative, cloud. Okay, something like that. 1 mark if they've got each one. Okay, right, so it's only out of 3 marks. They have to have the particle matched with either its charge or its location or both. Or if they have the charge but not the location. They just have the charge there? Well, they have the charge right, but the location is not right? No, then it isn't right. Okay? They have to have all the correct information beside the particle. Okay. All right, for number 4, which particle did J.J. Thomson discover? Electrons. Okay, he was the plum pudding guy. All right, who proved the existence of the nucleus? Rutherford. Okay, and that was the gold foil and photographic film experiment. Okay, and lastly, draw a picture of de Broglie's model of the atom. All right, well, if they have something like this, okay, like a nucleus, and maybe they put positives and neutrals or something in it, and okay, as long as they have a nucleus, and then they have a cloud, they're good. Okay, I'll accept that. That's what I want to see. Okay, it's out of 1 mark. If they don't have the cloud model there, or something that at least vaguely resembles the cloud model, okay, they don't get that mark. All right, so we are looking at, this is out of, yeah, here, 6, 7, 8, right? No, sorry, not 8. Sorry, we're out of 11. First question was out of 4. Okay. So give them a mark out of 11 at the top. Okay, you can let them see it, and then I would like you to bring them up to me, standing right here, and when you come up to me and give me your quiz, grab a Chromebook. All right, so what we're going to go over today, guys, is probably most of it will be review for you. Okay, from Science 9, you learned how to name ionic and molecular compounds. Okay, or at least went over it briefly. What we're going to talk about are the differences, first off, between ionic and molecular compounds, how they work a little bit, and then how we do the naming. So the basic naming will be a review, but there are a few other things that you probably didn't learn in grade 9 science that we're going to add on for certain types of special compounds. Now, I gave you guys your periodic tables yesterday, right? Okay, you're probably going to need those at some point today as well. All right. Key points for today. You have to be able to identify. I couldn't tell you. I put page numbers on there, but I don't really look at them. It's just lesson 2. So go right after from yesterday. So identify a compound as ionic or molecular. I mean, you can't name it properly if you don't know what kind of compound it is because the compounds have different properties. Okay? And then write formulae and proper names for the chemical compounds. Formulae is actually the plural of formula. Formulas is not a word. Okay? It's one of those weird ones. Okay, so ions and ionic compounds. Something is an ion if it has a charge, okay? And that can happen. Remember that electrons are not stuck in the nucleus. And sometimes in a chemical reaction, an atom may lose or gain electrons. And if that happens, it will either have more protons than electrons or less protons than electrons, okay? The number of protons, remember, can't change. Okay? Number of neutrons generally doesn't change because those things are stuck in the nucleus. Okay? But the number of electrons can, sometimes by a large number. Okay? Some things are capable of losing like up to 5 or 6 electrons, okay, in a given reaction. It's not common, okay? But most lose between like 1 and 3 electrons or gain between 1 and 3 electrons in a reaction. If that happens, then they will have a charge. Okay? All right, so an ionic compound occurs when a metal, and metals are all on the left-hand side of the periodic table. The periodic table is split not directly in half, but split into 2 by the staircase. Okay, the staircase runs, okay, from boron, and then it staircases down, okay, to polonium. Okay, so it runs on there. Anything to the left of the staircase is a metal. Anything to the right of the staircase is a non-metal. Okay, now that doesn't mean that all nonmetals are gases. Okay, they're not. There are some solid nonmetals. They're just not metals. Okay, they're like, I mean, if you look at what carbon looks like, if you've ever taken a charcoal briquette, okay, you had a bunch of carbon there. It's not metallic, but it's solid. Okay, everybody follow there. Everything to the left is metallic. Okay, so these things will react and they form a new molecule in simple whole number ratios like Dalton said. Okay, in these molecules, electrons are typically lost by the metal and gained by the nonmetal, which means the metal will now have what kind of a charge? If the metal loses electrons, its charge will be positive, okay? Because it'll now have more protons than electrons. The nonmetals typically gain the electrons, so they have now a negative charge because they have more electrons than protons, okay? All right, now the reason for this is that everything wants to have a full outer shell of electrons. Okay, this goes back to the Bohr model. The Bohr model explains ionic bonding better than the de Broglie model does, even though we know the de Broglie model is actually how atoms look. Okay, it's easier to see this happening on the Bohr model, right? So if I'm looking at a Bohr model of sodium, okay, so sodium is number 11 on our periodic table, right? Which means, okay, that sodium has 11 protons, okay, and it has 12 neutrons, okay, and how many electrons does it usually have? 11. Okay, now, according to Bohr, okay, and also kind of with de Broglie, okay, the closest orbital, or shell, can hold 2 electrons, okay? The next one out can hold 8. Okay, and then the next one after that can also hold 8. But we only need that shell to hold 1 for us to get to 11 electrons. Okay, everybody follow me there? Okay. In ionic compounds, the desire of every atom involved is to have their outer shell of electrons filled. If you're sodium, which will be easier? Losing 1 electron and getting rid of that shell and going down to the one below it that's full, or trying to find 7 more? Losing 1, okay? Which is why most metals lose electrons. It's easier. Their shell is less than half full, so it's easier to get rid of what they have than to find more, okay? Chlorine, on the other hand, has a shell that is 1 short on the outside of being full. All right, and chlorine's atomic number is 17. Okay, so I'm going to draw it a little bit smaller, even though it's bigger. Okay, so we've got 17 protons. Okay, and 35.45 gives us 18 neutrons. Okay, and so it's going to have 17 electrons. So we have that first shell that's got 2. Okay, we got the next shell. Now we're up to 10. Okay, and then we need this shell to hold 7. Easier for chlorine to pick up 1 or get rid of 7? Yeah, no, I've actually had people say, well, it's always easier to get rid of something. Yeah, yes, but this is like a puppy. Okay, you don't just turn it out on the street, you find a home for it. Okay, you have to find a home for 7 electrons. Okay, you can't just go and chuck it out though. Right? It doesn't work that way. Okay, so it's way easier to find 1 or get 1 more puppy, okay, than it is to find homes for 7. Okay, it's way easier to do that. Okay, everybody follow me there. All right, so these two get along famously because they each have what the other needs. Okay. Sodium's got to get rid of 1, chlorine's got to pick 1 up, okay? Which is why they react together very, very well. Now, these bonds, ionic bonds, are not very strong, okay? Molecular bonds are really strong between 2 nonmetals, but for ionic bonds between a metal and nonmetal, the bond is weak. The reason is they both got what they wanted. I know that sounds awful, but okay, they both got what they wanted. What do they need each other for anymore? Again, don't take that in a sociological perspective, but okay, that's kind of how it works. So now that they've done that, ionic bonds can split quite easily. But what happens is now you have ions instead of atoms that are floating around freely. Okay, this always happens in solution. That means essentially dissolved in water. Right? You don't typically see ions as a solid material. Right? So these things will just be floating around in solution. So now I've got a bunch of charged particles floating around dissolved in water. Okay, what will that water now be able to do really well? Conduct electricity. Okay, ionic mixtures or ionic solutions conduct electricity very well. Okay, you've probably all been told at some point that water conducts electricity, right? That's only partially true. Distilled water doesn't. Okay? Distilled water will not conduct electricity. Water is a molecular compound. Okay? It doesn't have charges that are floating around. But water is also the universal solvent, and it almost always has something else dissolved in it that does have charges. So tap water, lake water, river water, all that kind of stuff does conduct electricity because there's stuff dissolved in it. Okay? Everyone follow there. Okay? The more of that stuff you have, the better it's going to conduct. Okay? All right. Questions on how that works? Okay, so we'll look at the naming here. That's kind of how an ionic compound works. We're going to talk about ionic compounds even more next week before we start our prep for our first lab. Okay, binary compounds contain 2 things. Okay, so an ionic or binary ionic compound, okay, is going to have 1 metal and 1 nonmetal or 1 polyatomic ion, which we'll talk about later, okay, and a nonmetal or whatever. All right, so the name of a binary ionic compound is always going to be the name of the metal. Metal first, nonmetal second. You never change the name of the metal. Okay, in an ionic compound, the metal's name stays exactly as it appears on the periodic table. We change the ending of the nonmetal to "ide." Okay, so here's the general rule for naming simple ionic compounds. All right, so we could have magnesium oxide. All right, we could have sodium fluoride. We could have aluminum sulfide. What would I call this stuff? Sodium nitride. Does the 3 matter? Not for the name, no. Okay, in ionic compounds, the numbers make no difference. We never use prefixes on an ionic compound. Okay, so why don't we use prefixes? We obviously use them for molecular compounds. In fact, we have to. But why don't we use them for ionic ones? There's only one way sodium and nitrogen can go together. Because remember, when an ionic compound occurs, electrons are traded, and everybody's got to end up with a full outer shell. So there's only one way that that can happen. Okay? If we're looking at, if you look at your periodic table there, it has the charges of all the atoms written in, I think, the top right corner. Yeah. Okay. So sorry, top right corner. Okay. You can see that there's little numbers there with pluses or minuses beside them. Okay. If you look at sodium, sodium always has a charge of +1. Nitrogen always has a charge of -3. A compound has to have a charge of 0, because that means that all the electrons have been traded and accounted for. Okay? If nitrogen is going to get a full outer shell of electrons, it needs 3 sodiums in order for that to happen. You guys remember being taught that drop and swap, or swap and drop, whichever way they taught to you? It's the same thing in the end. Okay? So you take the 3, you drop it here, you take the 1, we don't write ones, we're done. Na3N. That's the only way those two can go together. Okay? In order to account for all of the electrons that have to be moved. Okay? That's why we never use prefixes for ionic compounds. Questions there? Okay. So remember, you do need to name both ions. And then this. I have oftentimes looked at that sentence and thought, I should make that 72-point font, underlined, italicized, because that is the one thing people mess up all the time. Okay? You never capitalize the name of a chemical compound. It is not a proper name, like John Doe. Okay? It is a chemical designation. That's not a name. We call it naming, but we probably shouldn't. Okay? It's not a proper name, so it isn't capitalized, but people have a terrible habit of doing it. Okay? I even catch myself doing it once in a while, and I've been doing this longer than you've been alive. Okay? It still happens because we're so used to capitalizing names. You'll get it wrong if you capitalize it. Okay? So don't capitalize it. Names are never capitalized. Okay? That is, unless you are starting a sentence with it, like sodium chloride is great on French fries. Then you would capitalize the sodium. Okay? But I can't imagine you actually writing a sentence like that at any point. Okay? All right. A true compound should have a net charge of 0. Okay? That's why we do the swap and drop, or drop and swap, or whatever you want to write it as. Okay? That's why that happens. Okay? The drop and swap assures that you have accounted for all of the electrons. Okay? Charges are positive on metals, negative on nonmetals, and it says there are equal to the group number, but we don't really use group numbers very much anymore. Okay? But you can, if you look on your periodic table, you'll see everything in group 1 is +1. Everything in group 2 is +2. Okay? That only works though for the representative groups. Okay? Through the middle, that's not true. Okay? When you get back over here, this is group 7A. Everything is a -1, -2. Okay, that kind of thing. All right. Yeah, you won't be able to find the charges for these ones because these are the metalloids. Okay, in this area, carbon can be a plus or a -4. Same with silicone. So we don't often include them. You don't see them in an ionic compound very often. That's why they don't have a charge, right? Like you almost never see a compound containing those 3 elements. An ionic compound. They're in molecular compounds all the time, but for some reason they just don't get involved with ionic stuff. Okay, typical chemical reaction. Aluminum. Is aluminum a metal or a nonmetal? Metal, right. Chlorine, metal or nonmetal? Nonmetal. All right, so we put those two together. Okay, chlorine is a special element. It always comes in pairs. Okay, when it's by itself, it always comes in pairs. Okay, when it reacts with aluminum, we get aluminum chloride. Okay, AlCl3. Has to be 3 because aluminum's charge is +3 and chlorine's charge is -1. So when you drop and swap, that's the number that you get. Okay, making sense. Okay, hopefully that's ringing a bell from last year. All right, I want you guys to try the first 5 on there. Write the names of the first 5 and really concentrate on not capitalizing them. I'll give you a few minutes and then we'll go over them together. Whoops. All right, obviously the first one's pretty easy because we've done it a few times already, okay? But we got sodium, we got chlorine, okay? So we are looking at sodium chloride. Please excuse my penmanship. It has always been bad and it'll never get better. All right, number 2, I've got potassium and fluorine. So this stuff is going to be potassium fluoride, right? All right, number 3, I've got hydrogen and iodine. Hydrogen iodide. Now, hydrogen often gives people trouble because hydrogen is a what? It's a gas. But it is also the most metallic element there is. Okay? It always wants to get rid of an electron. But it also could gain one and have a full outer shell. Remember, that first shell only holds 2. Okay, so hydrogen will sometimes act as a metal, and you will sometimes see it act as a nonmetal. It's weird. Okay, it is, after all, the simplest atom, so it can behave both ways. Okay, if it's listed this way, it behaves incredibly metallically. If you see it listed second, then it's behaving as a nonmetal, and it will then be listed as something hydride. Okay, so hydrogen can be a metal or a nonmetal. You have to look at where it is in the compound to decide whether it needs to be left as hydrogen or needs to be changed to hydride. Okay, everyone follow there. Right. Okay, for number 4, we got calcium and bromine together. What's the name of that one going to be? Calcium bromide. Okay, and number 5, we've got aluminum with astatine. Aluminum astatide. I am going to continue to say it aluminum, even though it has technically been changed to aluminium, which just sounds wrong. Because I've never had to go and recycle an aluminium can. Just doesn't sound right. Yeah. It's a European thing, that's why they changed it. But okay. So have a look at those. Okay, if you got any ones wrong and you're not kind of sure why, you can certainly ask. Okay, but let's have you guys finish off to number 14 there. Okay, I'll give you a couple of minutes, okay, to finish those ones off, and then we'll check and make sure we're getting them. All right, so on number 6, I've got cesium and sulfur. So this stuff is going to be cesium sulfide. And I don't care how you spell sulfur. Okay, I spell it with an F. Some people spell it with a PH. It's fine either way. Okay. Number 7, I've got sodium and oxygen. So this is going to be sodium oxide. Yeah, we really shorten oxygen. It's not oxygenide. It's oxide. Okay, and there's a few weird ones in there that when we put the "ide" ending, we actually shorten the word a little bit. Okay. That's not a capital S. I know it looks like it, but it's not. Okay, then I've got barium with selenium. Yeah, it can be selenide or selenamide. Either one is fine. Okay. I always write the shortest one because it just seems to be more efficient. Okay, number 9, I've got radium and tellurium. Radium telluride. And number 10, I've got lithium and fluorine. Lithium fluoride. Okay. All right, give you another minute or two to get done 14 there. Okay, so let's do the last 4 here. I got rubidium and sulfur together. Rubidium sulfide. Okay, number 12, we've got strontium and iodine together. Strontium iodide. Whoop, that's not a W. Okay, calcium with oxygen, calcium oxide. Okay, and magnesium with selenide would be magnesium selenide. And I can't spell today. Okay. How are people feeling with that? Okay. We will spend, probably tomorrow working on some more naming, because obviously we haven't gone over multivalent metals yet, and we haven't gone over molecular compounds yet. So I'm just going to give you a quick intro to the multivalent metals. Okay. If you look in your periodic table, okay, and you look kind of in the middle area, okay, especially like with iron's a good example, okay, you'll notice that a lot of those metals in that area have more than one charge listed. Okay, that is because they can lose different numbers of electrons. Sometimes they lose 2, sometimes they lose 3. It all depends on which form of the iron you're dealing with. One is more common than the other. Okay, on your periodic table, the first one listed from left to right is the most common charge. Okay, so if we're looking at, let's say iron, the most common charge for iron is +3, but it also has another charge of +2. Okay, for copper, it's the same thing. It's 2 and 1. Right? There's a bunch of metals that we call multivalent metals that can lose more than one electron. And you're probably thinking, so I'd still name them. Right? It's gonna be like iron oxide. Well, there's one problem with that. Okay, and the problem with that is iron oxide could be that, or that. Okay, based on the fact that iron has more than one charge. Okay, if I'm looking at iron with a 3+ charge, it goes with oxygen like this when you drop and swap, because oxygen's a 2 and iron's a 3. But if iron is a 2+ charge, it goes together like this. This is a 2, this is a 2, and they balance out. Right? So what's the problem with them having the same name? Right. And if you wrote it down and so you were talking to somebody about how you were doing this experiment that involved, taking iron oxide and injecting it into people with iron deficiencies, okay, someone might use the wrong one. And that could be a problem if this is rust and this is highly poisonous. Okay. It makes a difference now, right? Okay, or this one is rust and this one's highly explosive. Right? I mean, they're not. Okay, but I mean, let's just say that that was the case. You need to be able to communicate which version you're working with, because it means a different compound with different properties. Okay, and that can be a real problem. So when we're naming them, we have to somehow show in the name which charge we're dealing with. Otherwise, they both look the same. They both look like that. So what we do is we use a Roman numeral. Okay, we use a Roman numeral on the metal to show which charge we used. Okay, so in this case, this stuff is iron Roman numeral 2 oxide, where this stuff right here is iron. Wow, I think I need to calibrate my smartboard. I know my penmanship's bad, but that's just, yeah, that's what it is. That we'll say that anyway. Yeah. Iron 3 oxide. Okay, we just write a little Roman numeral in there to let people know this is the iron with the 3+ charge, so you get the formula right when you drop and swap, and then you know, in fact, which compound you're dealing with. Okay, so how do I figure that out? Well, I can look at this compound and go, all right, so there's 2 irons. But iron can have more than one charge. But oxygen always has what charge? It's always -2. All right? So you always look to the non-metal for help. All ionic compounds have to have a charge together of 0. Okay? How many negative charges do I have here? I have 6. Every oxygen is a -2, and there are 3 oxygens. Everybody follow me here? So in this compound, there's 6 negative charges. So there need to be how many positives? 6. So what charge does iron have to have if there's only 2 irons? 3. Okay, so this is the 3+ iron. Now I know what Roman numeral to use. Now, a lot of people just look at that and they go, well, couldn't you just reverse the swap and drop? Yep, and 2/3 of the time you'll be right. But remember, when we drop and swap, we also reduce sometimes. Like you would never write a compound that was A2B4. You would always reduce. And if you are using a reduced one, you won't get the right answer. All right, we'll see you guys tomorrow.